Okay, Assalamualaikum warahmatullahi wabarakatuh. Let's continue to the second reactor in the Aspen Plus, which is a reactor kinetic. Yeah. There are three types of reactor that we can simulate in here, which is reactor CSTR, reactor plug, and also reactor batch. CSTR is to model a continuous stirring reactor. Our plug is to model the plug flow reactor, and the reactor batch is to simulate the batch reactor or semi-batch reactor. In here, you can calculate the volume of reactor, the length of the reactor, the uh, decay time of the reactor, and also the conversion of the reaction. In a kinetic reactor, the the reaction equation is stored in the Aspen Plus as a global variable, and it is different compared to our yield or our stoic. If you still remember, or you can watch again the previous video, uh, the reaction is connected with the no, is inside the reactor block. If you still remember, yeah. If you add a equilibrium reactor, then in the R equal you have to specify the reaction. However, in the uh, kinetic reactor, such as our plug, our CSTR, and our batch, the reaction is separated from the reactor block. You have to specify the reaction itself outside the reactor block. And of course, there are so many types of the reaction, like the most common equation is power law and also the Langmuir equation. The Langmuir one is the more complex equation, which includes absorption and also the surface reaction and the desorption. So this one is the power law equation. Let's say the A plus B will produce C, and this one is the kinetic reaction equation. Kinetic rate reaction, A times exponential of minus E per RT times concentration of A times concentration of B. So this one is the common equation used in the power law. So this one usually denoted as K, yeah, K C A C B. So K itself contains A times exponential of minus E per RT. A in here usually described as a kinetic factor, yeah, kinetic factor, and this one, the E is activation energy, R is the ideal gas constant, and the T is the reaction temperature. So this one is the kinetic equation. This one is the reaction rate of a component. So that's why in here you can specify the information may be not minus RA, but it can also minus RB or RC. If the C is product, then you won't see any minus sign in here. So minus RA, minus RB, and RC. If the reaction is IA plus B becomes C. In a CSTR reactor, uh, it assumed to have a perfect mixing. Yeah, it is also not just perfect, but apa ya? Bukan hanya sempurna, tapi dia ya diasumsikan semuanya terjadi dengan ya, bahasanya bukan perfect, tapi nanti silahkan kalau ada yang ingat silahkan bisa dijawab ya, bisa diberitahu di grup. So the outlet reactor, the outlet temperature and also the outlet concentration is the same Continuous, no, not only, bukan perfect ya, tapi apa ya bahasanya? Kok lupa saya. Nanti silakan dicari ya. So the outlet temperature and outlet concentration is the same with the reaction temperature and also the reaction concentration inside the reactor. So the uh, input parameter for CSTR and the R plug is the same. The differences is only for the dimension of the reactor. In a CSTR, you have to specify the volume of the reactor, while the R plug, you have to specify the length of the reactor. The operation, it can be an adiabatic, isothermal, non-adiabatic, non-isothermal. So for the example in here, we have methanol with oleic acid. It can be reacted into methyl oleate and also water. Air, in this one is air in Indonesian language. So this one is water. So the reaction temperature is occur at 60 degrees C with the pressure of 1 atm. The kinetic rate of the reaction minus R, this one is minus RA, should be this minus RA, is equals to K times C methanol C acid oleate, oleic acid, where the Arrhenius constant or the kinetic factor is 0.0122, and the energy activation energy is 2600 joule per mole. The feed itself, it has 60 kmol per hour of oleic acid and 30 kmol per hour of methanol, and it is already at the reaction operating condition. And the property method used in here is Planck-Robinson, and you have to simulate this case by using CSTR. In Indonesian language, it is called reaktor alih tangki berpengaruh, and the translation of this language is CSTR, continuous stirred reactor, and also you have to simulate it in a plug flow reactor. And the specification is shown in here. The CSTR has a volume of 7,850 liter, while the plug flow reactor have a dimension of diameter 1 meter with the length of 10 meter. So you have to, if you calculate the volume of the plug flow reactor, it also has the same volume as CSTR in here. So if you calculate the volume of the plug flow reactor, the result will be also 7,850 or near with this volume. So in this theoretically, you have learned this in chemical reaction class, where which one is more effective? Is it using CSTR or using a plug flow? So you can calculate it manually, and you can also prove it by using simulation in here with the same volume. Which one is better? Which will give you a higher conversion of the product. Okay, let's start this simulation, and I have to clean it first. I will click new, blank, create. Yes, cancel. Okay, I already have the new simulation in here. Let us specify the, okay, no specification. Okay, so we have methanol, and then oleic acid. Oh, sorry, cannot be entered in here. I have to delete it first. In here I think we can write it on oleic exit. Okay, I put in here OA, and then methyl oleate. Okay, and then I name it MO, and the last one water. Okay, we have water in here. Click next, and the property method is Peng Robinson. Next again, we have one binary parameter between methanol and water. So if you remember to separate the methanol and water, you can use distillation column or flash, and it has an equilibrium uh, constant between this component. So the calculation of the parameter can be used to calculate the equilibrium constant is in here. Okay, click next, and we go to the simulation environment. In here we have one feed and also another two reactor. So we are going to draw something like this: one feed, two reactor, which are CSTR and plug flow. So, and one duplicator. This one is duplicator T101, and then we will put CSTR in here, R101, and then the R plug is R102. And we have the material in here, which is a feed. This one is R1 in. This one is R2 in. R101 out. Yeah. R102 out. Okay, done. We go to the stream, and for the feed itself, the condition is like this. The temperature is 60, 1 atm, methanol 30, and all exit 60. We have 60 degrees C, 1 atm, 30 kilomole of methanol, and the oleic acid of 60 kilomole per hour. Let's check it again. Okay, methanol 30, oleic acid 60. Okay, and then this one is the specification of the CSTR. Remember, in the CSTR, you only have a liquid phase that can be reacted inside the equipment. CSTR with the uh, vapor only, then it is almost impossible to react inside the CSTR. So you have to specify in here liquid only and the volume of 7,850. So we go to the block with the CSTR in here. The pressure is 1 atm. 1 atm. The temperature is 60 degrees C. And the valid phase, you have to change it into liquid only with the reactor volume of 7,850 liter. In here, the kinetics, we don't have anything in here. So you have to click new, R1, okay. And in here, you can choose which which kinetic model you are going to use. It will depend on the information of your case. In this case, we have a power law model. So you choose power law and okay. So see, in here it is quite different from the previous simulation. which use R stoic and also the R equal. The reactor in here, the kinetic in here only shown with the symbol of R1, but you have to specify the reaction at a different block. So first, before we enter the information for the R1, we go to the specification of the plug flow reactor. The specification of the plug flow reactor in here, let's go to the Aspen, the PPT plus. In here, the reactor type is a reactor with the specified temperature, which means that the temperature inside the reactor is not changed. Yeah, will not change because based on the reaction type, either this one is an endothermic or exothermic. So the reactor temperature is maintained at the 60 degrees C. Reactor with the specified temperature, constant with the specified reactor temperature 60 degrees C. For the configuration, in here you can also specify that if the reactor has a multi-tube inside the reactor, if there are so many tubes, then you can just click in here and then you type how many tubes inside the reactor. If no, then you just remove the tick in here. And then if the diameter is varies along with the length of the reactor, you can specify in here, and then you can specify the diameter as a function of the length in here. If not, then you can remove this one. The length is 10 meter and the diameter is 1 meter. Hey, don't forget to change the process into liquid only. The reaction also, we already have R1 in here. Since the reaction has the same reaction with the CSTR, then you can just move it to the right. So you can divide so many reactions in the Aspen Plus, and you can choose which reaction you are going to use at the different reactor. So in here, since the reaction is the same, then you can just move it to the right. Okay, finish. I think I have to go back to the case in here before we enter the information of the reaction information. So in here at the bottom of the below the utilities block, you see reaction with the red sign, means that you have to enter the specification of the reaction in here. You click R1 and then go to the input. In here you can click new. See, this one is to specify the chemical reaction. How many reactions do you have? Let's say in one reactor you only have 5, then you specify in here, and the another reactor you have 8 reactions, and you can specify 8 reactions there. And this one, the reaction is between methanol with the oleic acid becomes methyl oleate with the water. So in here, we not only have coefficient, just like the previous simulation with the non-kinetic model. In the kinetic model, you have to also specify the exponent, not only coefficient. For the coefficient, I think you still remember, it will depend on the stoichiometric reaction in here. The uh, you have to make sure that the mole of the reaction is already in a stoichiometric condition. I think in this one it's already fixed where the methanol is one mole of methanol, 1 mole of oleic acid becomes 1 mole of methyl oleate and also 1 mole of water. So in here you just put it 1 1 1. And how about the component? How about the exponent? The exponent is depend on the reaction of the kinetic rate. Yeah, the kinetic rate reaction. In here, the concentration of methanol is um, the power. pangkat ya, pangkat power of the methanol is 1. See, in this equation, I can also say like this. The minus R equals to K times concentration of methanol power 1, right? Only 1 in here. And times concentration of the oleic acid power 1 also. So we can write the exponent of the concentration of methanol and concentration of the oleic acid in here. The exponent of methanol 1, oleic acid is 1. However, the methyl olate and water did not appear in the kinetic reaction, so you don't have to fill any number in this exponent. Okay, is it clear? So that the coefficient is based on the stoichiometric, while the exponent is based on the kinetic rate reaction equation. This one, huh? In here, the exponent for the methyl olate and water is 0. And this one is the kinetic specification. Okay, let's go back to the aspen. Let's close it. Once you enter a reaction, then the kinetic factor will appear in here. In here, yeah. You have to fill in any information related to the kinetic rate of the reaction. So in here, the okay, go back to this one. The K is this one for this equation. K is A times exponential minus E per RT, which means that this A 0.0122 is the kinetic factor in here. It is the same equation in here. K times T power n exponential minus E per RT. It means that K equals to A in the PPT slide. Ya, jadi nilai K sama dengan nilai dari Arrhenius atau kinetic factor yang tadi nilainya adalah 0,0122. 0,0122 0.0122, and if in the equation did not include temperature, then the n should be 0, since the T power 0 will become 1, and the energy activation energy is 2600 joule per mole. 2600 joule per mole, or kilojoule per kilomole. It is the same. And make sure that the basis is molarity. Yeah, the basis is molarity. It might be different. It will depend on the kinetic reaction equation. In here, the equation is C. C means that this one is the concentration, and the concentration is molarity. If the equation is P, Papa, it means that not that one is not a molarity, but it may be a partial pressure, or maybe the equation will become M, which is mass fraction, or N, which is mole fraction. So there are so many possibility on how to write down the kinetic rate of reaction. And also in here, you can also change, is this reaction is in a liquid phase or vapor phase, or liquid and solid phase. And also the red basis, you can also change this one into catalyst. So if you reactor, if you want to simulate a reaction in a reactor with the catalyst, such as PBR. PBR is a packed bed reactor. where the physically it looks like a plug flow reactor, but inside the reactor you fill it with the catalyst, full with some amount of catalyst, so that you can the reaction is not only based on the length of the reactor, but it is based on the weight of the reactor, based on the volume of the reactor. So volume and weight, it can be connected with the porosity, yeah, the porosity of the reactor. Okay, that's all. I think we already input every information for the reactor. Then you just simulate. No warning, no warning, no warning, and then you can check the result summary in here. You can calculate the conversion of the CSTR and also the plug flow. Okay. The question is, how much is produce higher ammonia between CSTR and the plug flow? Oh, sorry, not ammonia, methyl oleate. The methyl oleate, you can see in here, with the same volume of the reactor, you can see that R2 produce more methyl oleate compared to the R1. R2 is the plug flow reactor. It is just theoretically correct, where the sometimes when even you put three series of a CSTR reactor, is somehow it can be equals to the 2 or 3, yeah, 2 or 3 series reactor, it will be equal to one plug flow reactor. Okay, I think that's all for the introduction of the reactor. For the assignment, I will show you one of the I want you to make a simulation of a reactor based on the chemical reaction engineering book, handbook, any handbook. You can find any handbook of chemical reaction engineering which includes a kinetic reactor. You can choose either using CSTR or plug flow, or you want to do both, it will be better. Or you want to, or I haven't teach you to do the batch reactor, but it is also quite easy. But you can also try to use batch reactor simulation. Any handbook, not only assign, you don't have to solve the exercise. You can also choose the example from the handbook. If there is an example in the handbook, and then there is a calculation of CSTR and R plug flow reactor, which include a kinetic factor or kinetic reaction rate, then you can use it, and then you can simulate it, and then you can compare it with the result. So I want you to make the report, yeah, in a Microsoft Word, stating which example, the example that you use, and then the source also, which book, which pages, and which one is the you are going to use for the example, and also the answer in there. And then after that, you simulate it using Aspen Plus and compare the result. Did your result have the same answer with the example or not? So I think that's all for the uh, Aspen Plus unit of the reactor. Thank you for your attention, and see you next week. Assalamualaikum warahmatullahi wabarakatuh.